Okay, so our next speaker is Aloizio DaSilva. Aloizio is the director of the XG Testbed here at CCI and leads the OTIC for the Washington metro area. So please welcome Aloizio.
Okay, thank you, Paul, for the kind introductions. First, I would like to thank you guys to join the srsRAN team and also Virginia Tech to this workshop here in Washington DC metro area. I am very glad to host the srsRAN workshop in here. The story that I'm gonna go to tell today to you guys is basically is a journey that took me to join Virginia Tech and the Commonwealth Cyber Initiative to build the CCI XG Testbed. CCI, for those does not know, is acronym for Commonwealth Cyber Initiative. That is an initiative for the Virginia state local government that is very focused on autonomous systems, intelligent, and also workforce development and cybersecurity. Basically, the CCI XG Testbed was born in 2020 when Virginia Tech hired me to lead the large-scale deployment of Testbed across of Virginia State, considering the whole network of the Commonwealth Cyber Initiative. And this testbed, the CCI, was building based with our own resource came from the Commonwealth Cyber Initiative that is not funding come from the industry or from National Science Foundation. And the main focus of this testbed in the beginning, 2020, was basically to build a 5G non-standalone and a 5G standalone platform, okay, end-to-end open source to support the CCI research networking. However, I start to realize that we need to diversify and also capitalize in such a way that we can retrieve, or you call all the return on investment that you have to build this infrastructure, both indoor and outdoor. Okay, in these directions, to trying to capitalize and get back the return on investment that we have done, okay, we decided also not just to support the CCI research networking, but also support the government interest in research and the use case, also support industry partners that want to collaborate, validate, and do experimentations in a stable platform. But also, that was the most important. The CCI XG Testbed was created under the umbrella of our university and academia, Virginia Tech. And as a leader and a advanced wireless communication research, we believe that we also need to use this platform that we have built indoor and outdoor to create what we call the workforce development. And then we use the platform that we have as well, okay, to teach students, MS, undergraduate students, the overall full stack of advanced wireless communication networking. And one of the reasons that we decided to invest and workforce and development and build these infrastructures and support the people that are interested in wireless advanced networking is because there is a lack of qualified personnel in the advanced wireless communication field. Many of you get a lot of the students that come to us today, the majority of them, they don't have hands-on experience. Some of them, they have a very good background in theoretical, but when you ask them, can you use this new mechanism that you have developed and theoretical, this amazing machine learning technique, can you embed this in our network infrastructure, in our testbed, and really show amazing proof of concept that your mechanism will work both in a simulation environment, in a controlled environment? They are incapable to do that. right? Then we envision to use the CCI access to testbed as a venue to support the workforce development, but more focused and the experimentation piece, not only in theoretical. Given that, as a result, okay, we were able to create here in Virginia State and Washington DC metro area, what I like to call a transformative infrastructure, right? It's a transformative infrastructure. Why? Because we are able to support research, experimentation. We are capable to support government use case. We are also capable to work and support industry interests and objectives. And what the most important, we are able to support and contribute for the workforce development. Given this, we create what we call this transformative infrastructure, that is the Commonwealth Cyber Initiative XG Testbed. Okay, because we want to work beyond 5G. We want to support as well 6G and the next generation of telecommunication network. And to realize and to accelerate, okay, mainly the open radio access network. And because of this, the path that we have building and walk together with my team, with Virginia Tech, we are today, we have been designated as an open testing and integration center in the Washington DC area to support and accelerate the O-RAN deployment across of others across of the country. Also, we are capable to support advanced communication network experimentation, going from the application layer to the physical layer. And of course, we are ready to support as well the 6G and beyond. Given that the CCI XG testbed is divided in two sites, indoor and outdoor. The indoor testbed is in this building, is in the 3rd floor, where you have the radio ceiling network. You guys are welcome if you want to know. After the break, during the break, you can talk with me. I can escort you upstairs to see the testbed that we have there. And the outdoor piece, okay, is located 226 miles from here, 4.5 hours from miles from here, and Virginia Tech main campus that is located in Blacksburg is our outdoor deployment. I will walk you guys through to each one of these sites. Here's the first site, okay, that is based indoor, is a radio ceiling radio network, okay, where you have 72 software-defined radio from National Instruments, the last generations of is a combination mismatch of X310, X410, and N310. We also have the B205 Mini and also the B210, but they are in the rack, not in the ceiling. All this infrastructure is basically accessible remotely. We provide the VPN credentials and you have access to SSH. We operate over there, of course, using the FCC experimental license that we have, okay? And our main cellular stack, since the beginning, we have tools and we have a close partnership and relationship working with the srsRAN team. Our base cellular telecommunication network in the beginning was srsRAN 4G LTE and 5G stack that is using for research, testing, and validation. I would like to mention here that today I have under my umbrella, I advise 10 students, 6 MS students and 4 PhD students. All of them are capable to deploy their own 4G LTE networking and their own end-to-end 5G networking using open source software. And the end of their thesis, the objective, they need to deliver as well a real proof of concept, a small scale that is part of the testbed. I don't accept simulations. I don't accept theoretical work. The theoretical fundamental research needs to be applicable to our testbed. This is just a high-level diagram of the ceiling network that we have upstairs in the 3rd floor. All the 72 USRPs is connected to multimode fiber 10 gigas to our rack room equipment, where you have a bunch of servers, and basically is where we hold our cloud environment that is also open source, is based in OpenStack, okay, where we dynamically provide the virtual machines and containers that can support each one of the software-defined radio that you saw in the ceiling. Given that, experimental users can just access remote and they can do whatever they want. They can deploy as a stack, cellular stack. They can deploy srsRAN. They can use GNU radio. They can use as well OAI. And of course, we hold as well the full stack that I'm going to talk later, the end-to-end of our O-RAN ecosystem that is also end-to-end open source in our testbed. And all these radios are synchronized. We have a GPS antenna on the rooftop of this building that is connected to 2 octoclock master. Okay, all the USRPs, they are also connected to octoclock that allow to do time synchronizations and enable you to do, for example, Massimo MIMO kind of experimentation. Just I will not dive deep here, but I talk a lot about the infrastructure by itself, software-defined radio, SRP. We also have been working very strongly in the software piece because we need to integrate everything. And as you can see here in this slide, everything that we do in this CCI XG testbed is basically end-to-end or O-RAN based. We have enabled, today we have the non-real-time RIC from the O-RAN software community, full operational in our testbed. We also have the near real-time RIC from the software community, also fully operational in our testbed. We enable the dashboard of the non-real-time RIC that enable you guys to develop a mock versions of the RAP, because in the O-RAN Alliance today, RAP is still on the specifications, but we are able to develop a containerized mock versions of the RAP and onboard this in our non-real-time RIC dashboard and using the radio ceiling to do experimentations. We also have the near real-time RIC dashboard that we have done some modification with that allow you to bring to our testbed your own XApp, okay, on board through this dashboard and use our radio ceiling network to do experimentations. And of course, the most important piece of the O-RAN ecosystem is how you can embed the intelligence in the network infrastructure, right? To do that, we need to integrate to the O-RAN ecosystem in the service manager orchestrations in the upper layer, what you call the AI/ML framework. We also are working very strong and two open source AI/ML framework. One of them is the ClearML, and the another one is the AI/ML framework that is part of the O-RAN software community. Today, we have integrating our testbed, the ClearML, that allow us to capture data, collected data from the O1 interface that is sent from this AI/ML framework, ClearML, that is training then and generate a data model that is then packaged or containerized and sent for a specific interface that we create using Kafka, okay, to the non-real-time RIC, where these arrive, the data model arrive there, we pack again, containerize this, and we call this data model on a RAP. That also is capable to talk via A1 interface to the near real-time RIC, okay, and activate the XApp to modify and eject any policy that came at the upper layer to the radio access network. In our case, as I mentioned before, the radio access network, we have been using 4G LTE from srsRAN and also 5G CU and DU monolithic from srsRAN. And so far has been worked very well and is very stable for us. And we are able to modify the RAN using a RAP and XApp when they communicate with each other. There are other building blocks here that we are still working. One, for example, this one in yellow here, that is control framework, because we know that the Open RAN is focused in radio access network. However, we are focused in the overall end-to-end architecture of the cellular telecommunication network 5G. And because of this, we want to enable in the O-RAN ecosystem also how you can work with 5G core. Because the 5G core as well has several virtual network functions containers that can move across of the network, right? And then we are developing as well, working this control framework that allow us to work as well together in the O-RAN ecosystem with the 5G core. some examples here. In 2012, we have the Mobile World Congress that we present for the first time an end-to-end O-RAN ecosystem focused on the software-defined radio, where you have the non-real-time RIC with ARAP, we have the near real-time RIC with XAP, and non-real-time RIC integrate with near real-time RIC via A1 interface, and then using 4G LTE and the srsRAN. In this showcase, in Mobile World Congress 2022 in Las Vegas, we use a use case to illustrate what we have deployed in the background. That was a first responder use case, okay, where we took 2 cell phones, okay, and we connect. One cell phone was a common users, a general users, and another cell phone was a first responder. And in our network, the general user is always connected to this end-to-end O-RAN ecosystem network. But when the first responder, because a scenario of emergence, arrive to that area, what the ARAP that we have developed and that XAP does, the ARAP detected that the first responder in the area, okay? And then he trying to communicate with the XAP to trying to allocate more resources of the radio access networking to the first responder without disconnect the general user. But when the first responder is done with his activity, surveillance, and is out for the area, we reassign more resources for the general user again. Again, this year, we also have a presence in Mobile World Congress Las Vegas. Thank you for National Spectrum Consortium that enabled us to be there with a booth. But this year, we came with a different approach. Okay, this year, we demonstrate their end-to-end O-RAN ecosystem as well. But this time, it was not focused in 4G LTE, was focused in 5G using srsRAN, CU, and DU. And in this case, we work together with srsRAN team to enable to change the PRB, the physical resource block, in their srsRAN code. And then we develop an ARAP, an XAP, that allow to change the PRB based on the demand of 2 COTS UE that was associated in the demonstration Mobile World Congress Las Vegas. Also, we have a virtual presence in Mobile World Congress Shanghai, where we demonstrate as well a closed loop end-to-end O-RAN managed for near real-time and non-real-time RIC demo using AI/ML as well. Also, as I mentioned earlier today for you guys, we are focusing workforce development, mainly the radio grid that we have upstairs. This is a good example. In 2021, I was able to organize and here together with CCI, what we call CyberCamp. We brought and select a couple of students from Virginia State College, undergraduate students. We brought them to our testbed upstairs, and we make available the full radio grid network in such a way that they can do the following activities. First, we work together with them to deploy their own end-to-end 4G LTE using srsRAN SDR base. Using COTS UE, use SDR as well as UE. Then we design an attacker that was inserted in their networking. And we ask them, during the week that they spend here with us, they need to figure out where the attacker was happened, okay, what the building block that was compromised, and what solution they are gonna do to stop the attacker. And this was an amazing thing because these people, these students, they have never thought to create their own cellular network. They have no idea how exactly a cellular network is divided in these 3 layers that you have the core network, you have the radio access network, and you have the user equipment. The second site of the CCI XG testbed is what you call the Strobo Creek CBRS network. CBRS stands for System Broadband Radio Systems, okay? For those that is not familiar, okay, in US, there is a band that operates between 3.5 and 3.7 gigahertz. That was the first band that the FCC has released to do spectrum sharing in US, okay? And then this is called CBRS. Then we are building outdoor, we have this test bed in Virginia Tech main campus that I will walk you guys through. And Virginia Tech and via FCC auctions in 2020, we have bought a spectrum from a commercial spectrum from CBRS. Then Virginia Tech bought 8 blocks of 10 megahertz each. 4 blocks of 10 megahertz is located in Virginia Tech main campus, and the other 4 blocks of 10 megahertz is located in Montgomery County, that is the border of Virginia Tech main campus, where Virginia Tech has located several farms laboratories. And then this is a perfect environment for us to deploy our own CBRS private network and also deploy a real environment, an experimental network using the commercial license that we have. Okay, and in these directions, we start to build then under my responsibility together with Virginia Tech Institute of Technology IT team to cover a blueprint to explore and exploit the CBRS spectrum that we have. For this, we are building there 1.5-mile corridor with true locations in the rooftop of strategic buildings on the campus. That in this corridor that you are seeing here, we have 3 main areas important for us. We have Virginia Tech, the drone park, that allow us to do experimentation with drones. We also have all the farms laboratory that is located basically in the #1 location. Okay, and then we have the Strobo Creek Park that is located around of the #2. And in this Strobo Creek, the reasons that we choose this area, this 1.5-mile corridor, because there is a creek that flow underneath of Virginia Tech campus, and there are seasons that this creek flows and really reach the residential area of Virginia Tech as well, and people cannot walk that, cannot pass. And then we make this choice because to validate our CBRS network deploying there, we are deploying a use case that is based in IoT to do flooding monitoring of that area. That in the same time, we are contributing for the community that live, that use that area, but in the same time, we are create a very attractive use case for validate our infrastructure deployment. I don't know if you guys are familiar how the CBRS structure work and FCC, but CBRS ecosystem is composed as well for 3 layers. We have the spectrum access system that is authorized by FCC, some entity US that is responsible to do the spectrum sharing. Today you have 2 entities in the US. You have Google SAS, okay, and you have Federated Wireless SAS. Federated Wireless SAS is located 2 blocks from us here. And this is the first end. However, for us do experimentations in developing the end-to-end CBRS ecosystem, Google SAS, Federated SAS, they are commercial productions. They will not allow us to inject a new mechanism to do a spectrum sharing in their production environment, in their SAS environment. Okay, then to solve this problem, Virginia Tech came with a brilliant idea to develop what we call an open SAS, okay, an open source SAS spectrum access system. And then today, I should say that we are the first test bed that is capable to provide end-to-end experimentations indoor, in lab, and outdoor, or, okay, to do end-to-end experimentations in the CBRS ecosystem using our open source spectrum access system, using also what we call the CBSD. CBSD are the CBRS base stations. We also, I will talk later, we have building, okay, in our lab. I think you guys have seen one of my students in the corner in the back with a big antenna con scope commercial there. That one is our prototype for the CBSD or CBRS base stations that we are deploying outdoor in Virginia campus, main campus. And that base stations is fully based in the srsRAN 5G network, okay, stack. Then, as I mentioned, we have also FCC license to operate, and then we are using srsRAN 5G CU in the U and TDD mode for CBRS. Just to talk quickly here, as I mentioned before, we have building our own open source spectrum access system. Is available for download. Everyone can use. We are continue improve it. I should mention that initially this spectrum access system was the first version was developed as part of an MS thesis of a student of Dr. Carl Dietrich that is located in Blacksburg. What we have done, we have got the code that this student has done, and we have made this spectrum access system we call OpenSAS, complying with the FCC specification, that there is a standard group that is called WinForo. We make the OpenSAS complying with the WinForo as well. Then we change a lot of things to be standardized. And then you guys should ask how you have tests that is complying with the standards. I will talk this in the next slides. This is, you can see there is also a graphic user interface that my student has developed to make things more visual, to see how the spectrum access system happens. In his demo there, you guys can check the GUI from the OpenSAS system. As I mentioned before, we have developed the CBRS base station prototype that also is there, you can check. And both of the CBSD and the OpenSAS are both complying with the WinForo specifications. And the way that we have tested this is the following. I have a project in collaboration with Google, and Google has enabled for us their Google SAS test environment, okay, to test our CBSD prototype that we have developed here at Virginia Tech. What we have done, we just got our CBSD, and we try to connect our CBSD with Google SAS. To do this, there is a process around 12 steps that the CBSD need to pass to be allowed to transmit in CBRS spectrum. And our prototype based in srsRAN was capable to match all these steps and be registered in the Google SAS test environment. This means that our CBSD is compliant with the WinForo specifications, despite being soft-defined radio that is not allowed for FCC to transmit, unless in the experimental environment, okay? And also, we got that the same result that we got from our OpenSAS system, open source spectrum access system, we got when we connect with the Google SAS. This means that we have today a fully complying WinForo specifications with our open source CBRS ecosystem in our testbed. Here is just to highlight that we have one site is here in this building, the indoor lab. The another site is in Blacksburg, Virginia Tech, and they are apart from each other 264 miles. And then they are connected through a multimode fiber as well, 10 gigas. Last, here from I would like to highlight as well a little bit that we became 3 months ago a URAN OTIC at Washington, DC metro area, okay? This OTIC application was basically supported by AT&T, Verizon, and Dish Network. They are co-hosts of this OTIC center in Washington, DC metro area. Our OTIC center has been complemented for 4 other laboratories across of Virginia State. One laboratory is located in north of Virginia, where is Virginia Tech, the main campus, with wireless at VT, that is led by Dr. Jeff Reed. Another laboratory is located in north of Virginia in George Mason University, that is led by Dr. Vijay Shah, is part as well. And another laboratory that contains some Ericsson network outdoor is led by Old Dominion University, that is led by Dr. Sachin Sach. And of course, then we have the Virginia Tech, the southwest of Virginia node, that is Virginia Tech, that with wireless FVT. And of course, here, Commonwealth Cyber Initiative, we are the lead host for the OTIC Center. Our vision from the OTIC Center that I have been advocate and all the face-to-face ORAN meetings, all the meetings that I have attended, with ORAN is that we want to be a center of our excellence and Washington, D.C. metro area and then Virginia State for research and development, innovations, and ORAN, okay, to support U.S. government use case, mainly by the fact that we are in a very strategic location, close to all the U.S. department. Here is very easy for them to do a walkthrough to my door. Also focus in workforce development and advanced wireless communication with hands-on experiments, not just theory. And of course, meet the mission that ORAN Alliance is expected for our OTIC Center, Washington, D.C., that accelerate the end-to-end ORAN deployment and testing. Basically, the focus of our OTIC Center here in Washington, D.C. is mainly focused on conformance testing, performance tests, and interoperability tests. Despite that, we are doing also a lot of work in security in the ORAN ecosystem. But for now, for this first year, our focus is just conformance, performance, interoperability testing. We have no goals at short term to become a certification badge for ORAN Alliance, but for long term, this will be a reality, but not now. I am open for questions.
Thanks very much, Aloizio, and I should especially thank Aloizio as the catalyst for helping us put together this workshop. Without Aloizio's help, it wouldn't have been possible. So I'm happy to take some questions.
I am Govind from ARM. Can you go to your slide 18 on the end-to-end test, performance test? So because you're using next one, 18th one, last but one before 18, 1.8. The question is about, can you go to the last slide? Yeah, next one. Yeah. So, so do you have a performance dashboard with different vendor RU, DU, CU running in your lab and showing a performance dashboard about how it performs when I actually deploy a SRS software in those hardware components?
Thank you for the questions. I forgot to mention, actually, today in our OTIC center here, we have not done yet any tests with commercial equipment yet. All the things that we have done so far is end-to-end open source using srsRAN, basically, and make sure that everything is complying with the ORAN specifications, is complying with the A1, is complying with A2 protocol, is complying with A2 service model. However, we have in our lab already DU for a vendor that I cannot mention yet, is outside from US. These vendors, they have developed their own SMO, Service Manager Orchestrator. They have developed their OCU, ODU, and their ORU. This vendor will be our first experiment here. The DU, as I said before, is already in the lab. We're gonna do with them first the integrations of their whole the equipment and the SMO component in our test bed. We're gonna do the validations of everything is integrations and these operations. After that, we move to the what you call conformance tests to make sure that what they have advocate for me, that their CU, DU, RU, SMO are compliant with the ORAN specification is really compliant. After that, we're going to generate a report based on the ORAN specification for testing. And we're going to first share the report testing, conformance test with them. And then follow up, we share with ORAN Alliance. After that, we're going to go to perform what you call the interoperability testing. I like to see the interoperability test at different two angles. There is interoperability test among the ORAN components, interoperability with non-real-time RIC, interoperability of near real-time RIC, right? And there exists the another angle of interoperability, that is interoperability across the disaggregated RAN, interoperability between CU, DU, and RU that come from different vendors. Then we're going to do interoperability with them first among of the O-RAN components, near real-time rig, for example, generate a report, share the report of O-RAN Alliance, and then do the same thing with later on with the interoperability across CU, DU, multi-vendor component.
Are there plans to integrate srsCI/CD with this testbed so that every code that gets checked gets?
Good question for Paul.
That will be great.
That's something we're going to look into. Please thank our speaker.
Thank you.